Hello everyone, this is Edward Doolittle. I am going to continue with my series of talks on Stat 100 Chapter 8. This one is going to be on Section 8.4, Interval Estimation. So interval estimation is the main topic of Chapter 8. We're going to be talking about the big deal here is confidence intervals. So we are fully into inferential statistics now that we're talking about confidence intervals. So confidence intervals are going to be very similar to what we previously talked about in section 8.2, which was point estimate plus margin of error. So basically, computationally, they're going to be pretty much exactly the same. But the concept here is a little different. So I'm going to try to explain to you the idea of a confidence interval, the concept of it, and then we're going to do some calculations, and we're also going to throw in another twist. So we're going to add in another change, another source of variability in these problems. And at this point, after we finish 8.4, we'll be well prepared to do pretty much any confidence interval type question. There are still some variations that we'll talk about later, but this is sort of the highlight of Chapter 8. Okay, so let's take a look at the situation we examined last section. So we had here a population mean mu somewhere on our x-axis, and now we take a sample size n, and we average the sample, so we're going to get x bar, and we do that a whole bunch of times. And we get a sampling distribution. So sometimes our samples are going to be below mu, sometimes they'll be close to mu, and sometimes they'll be above mu. And we know from Chapter 7, the central limit theorem, that distribution of different x bars that we can get is normally distributed with a mean of mu. So the sampling distribution is approximately normal. By the way, we are, of course, assuming that n is at least 30, so a large sample. Central limit theorem tells us that the sampling distribution is approximately normal with mean, mu, and standard deviation, which in this context we call the standard error, sigma over the square root of n. Okay, so that's we know all of that already. That is central limit theorem from Chapter 7. Now, let's say I do my experiment, and instead of mu, I get x bar, which is going to be, for me, it's going to be bigger than mu in my case. Now, there's kind of a funny reciprocity happening here. If my sample is within 2 standard deviations of mu, my sample mean is within 2 standard deviations of mu, then mu is clearly within 2 standard deviations of my sample mean. So it's kind of like a tit for tat. If x bar is close to mu, then mu is close to x bar. And that's pretty obvious. It's so obvious that it can actually be confusing, but it really is an obvious thing. And so what that means is that if I go 2 standard deviations from x bar, it will contain mu. And I like that because it then allows me to say something about mu. It says that mu is somewhere in this range. So I don't know mu exactly, but I do know something about mu. It's somewhere in this range. Right, so that is our kind of idea. We're going to take what we did in section 8.2 and just kind of turn it around a little bit. Now you do the experiment, and say you get this value for x bar in yours, and then you construct your two standard deviation interval around your starting point. Well, you're going to capture mu as well, because you were close to mu. That means mu is close to you. I like the way that rhymes. So your interval is different from mine, but it still captures mu. And so we do this a whole bunch of times. And Charlie does this, and Amy does it, and Bill does it, and Fred does it, and so on. And so let's say 20 different people do this experiment. 19 times out of 20, mu is going to be within their interval. So there's Fred. Fred started here. His two standard deviation interval captures mu, and so does Charlie's and Bill's and Ted's. Okay. However, Amy out here drew the short straw. She was just unlucky. It had nothing to do with her skill as a researcher, but just a matter of luck. And this is one of the messages here, is that sometimes purely by luck, we get a bad sample. We get a sample that isn't representative. And so Amy got the sample that wasn't representative, and she missed the boat on mu. So mu is not within two standard deviations of her x bar, of her sample mean. Because we are 95% of our measurements are within, 95%, not of our measurements, but 95% of our x bars are within two standard deviations of mu. That means 95% of the time we do this, mu is going to be within two standard deviations of our x bar. So we expect someone to be unlucky like Amy only one time in 20. So that means that we can say that 19 times in 20, mu is somewhere in our interval x bar plus or minus 2 standard deviations. Okay, and so that is exactly what we mean by a confidence interval. When we say this, we give an interval. Here's the interval right here. And then we can say we are 95% confident that mu is somewhere in our interval. And that is another way of talking about or of inferring information about mu. That we can now say a true statement about mu without determining mu exactly, but only taking a sample. Our true statement is a statement involving probabilities, so it isn't 100% true, but it's 95% true, which is considered to be appropriate for any kind of scientific investigation, or most scientific investigations. So if you are 95% sure of your results, you can then publish it in a scientific journal. So that is how confidence intervals work. Now, computationally, this is actually simpler than it may look. No, the explanation there, I know, can be a little bit confusing, and it's really simple, but it's hard to explain. So I don't know how else to say it. I'm just going to have to kind of leave it with you and say, for now, what I really need you to do is to be able to do the calculations, and then you can understand it. You can try to spend some time understanding it. You should really spend some time understanding it, interpreting it. But for now, we're just going to start with the calculations. And in terms of the calculations, they are very simple. So they are exactly the same as the calculations for point estimators and margin of error. So the confidence interval, 95% confidence interval. Is based on your X bar. And then to X bar, you're going to add or subtract, to go up or down. You're going to add or subtract one margin of error. And the margin of error is 1.96. I said 2 earlier, and I was just trying to make it sound a little friendlier, but really it's 1.96 times the standard error. And what is the standard error? Standard error is sigma over the square root of n. And the same drill, we don't know sigma, so it turns out that we can approximate sigma by s in the large sample situation. So sigma is approximately s, therefore sigma over the square root of n is approximately s over the square root of n. So that gives us how to determine a confidence interval, and it is exactly the same calculation as we did in 8.2. So let's take a look at an example. We'll start with an example from the textbook. So let's say a scientist who's interested. This is 8.6 on page 326 of my book. A scientist interested in monitoring chemical contaminants in food and thereby the accumulation of contaminants in human diets selected a random sample of n equals 50 male adults. It was found that the average daily intake of dairy products was X bar equals 756 grams per day with a standard deviation of S equals 35 grams per day. Use this sample information to construct a 95% confidence interval for the mean daily intake of dairy products for men. Okay, so let's take the information there. 8 points. Sorry, this is example 8.6. So the sample size is n is 50. And an important thing to note is that that is bigger than or equal to 30, so this is large sample. X bar is 756 grams of dairy per day. I kind of wonder about that. It sounds like an awful lot of dairy, but it's like well on your way to a kilogram of dairy a day. That's an awful lot of cheese. But anyway, we'll just take that data as given. And then the other thing that was calculated is the sample standard deviation, and that is 35. Last thing to note is that we want a 95% confidence interval. All right, and as I mentioned previously, these two numbers, X bar and S, are calculated, pre-calculated for you. It would just be cruel for me to give you raw data and ask you to calculate X bar and S in particular for 50, a sample size of 50. Because that would just be a whole lot of pounding away on your calculator. So it's not really a good use of your time during a test for me to ask you that kind of question. So I won't. Usually I will almost always, I can't think of time when I wouldn't, I will provide you with the pre-processed data, so X bar and S already calculated. All right, so what are we going to do with this? Well, we're gonna tackle it in stages. I am going to first find the SE. Formula for that is very simple. It is approximately equal to S over the square root of n. That is 35 over the square root of 50. That's going to be very, very close to 5, but let's get the exact result. It's 4.95, let's say. Okay, so that's our standard error for this situation. Now our margin of error, it's not exactly 2 times the standard error, but it's more like 1.96 times the standard error. So I just take the result that's sitting in my calculator and I multiply it by 1.96. I'm going to get 9.70. Okay, now our 95% confidence interval is X bar plus or minus the margin of error. Margin of error, the margin of error is 9.7 and X bar is 756, so it's 756 plus or minus 9.70. So that's two numbers. Plus or minus doesn't mean a choice, it means do them both. So I have to do, the interval is going to look like 756 minus 9.7 is the low end, and 756 plus 9.7 is at the high end. That's going to give me an interval. So let's do the calculation here. So 756 minus 9.7 is 746. 746. And I'm going to add 9.7, so that is going to be 756 plus 9.7 is about 766. So that range of numbers is my 95% confidence interval. And now we need to interpret it. So we can say that the mean consumption of dairy by men in the population is in the range 746.3 to 765.7 with 95% confidence. So we can say that with 95% confidence, or another way of saying that would be 19 times out of 20 . Right, and so we have to state that to be completely honest about our investigation. We're not 100% sure that the average dairy consumption is in that range. We're 95% sure. So that is how you calculate a 95% confidence interval. That's pretty much the same calculation as as a point estimator plus margin of error. However, it is conceptually a little bit different. Okay. So that is pretty much the heart of it, and you see, it's not really very difficult. The calculations are really straightforward, really simple. It's the interpretation of it that may be complicated, and that, you know, I really am going to insist that you write an interpretation for these confidence intervals, so you start to understand what they mean. The other part of this section, another part of this section is that we're going to start changing this 95%. We're going to change it and see what changes in our calculation, how our calculation can change. And so we're going to introduce a new variable here. So 95% is our confidence. And what we're going to talk about is 1 minus 95%. And that is a number that we're going to call alpha. So in this case, alpha is 5%. That means our confidence is 1 minus alpha, which is equal to 95%. So this alpha is a very important parameter, and we are going to talk about the meaning of alpha a little more in chapter 9. But for now, we're just gonna leave it as alpha. There's a good reason why we want to talk about 5% instead of 95%, which we will explore later, in particular in chapter 9. But for now, pretty straightforward. And the textbook, you'll see, sometimes says 1 minus alpha 100%. All this does is change that 90.95 to 95%. It's not significant at all. It just changes the symbols that we use to represent. You should recall that 95% and 0.95 are exactly the same thing. So this doesn't change anything except for the words that we use, the sort of the hot air that we're blowing when we say this. And just some people like writing 95%, and people who are not really that well versed in statistics will often talk in terms of percentages. But you'll see that if you go back through our notes, you'll see that we have mostly preferred the decimal, because we end up typing things into a calculator, and our calculator may not even have a percent button, so we just type 0.95. Anyway, 1 minus alpha is 95%, and that is exactly the same as 1 minus alpha 100%. They're all the same. It's just the expression that we're using to talk about it. Okay, so there's a name for this. It's called the significance level. So 5% significance means exactly the same as 95% confidence. So if you're asked to do a confidence interval at the 5% level of significance, it is exactly the same as doing a confidence interval at 95% confidence. And we've already done that, so you know how to do that. What we will change this number though. So we can change the confidence level in some typical values that we may see are 90% confidence, 95% confidence, 98% confidence, and 99% confidence. Never 100, of course. In each of these cases, we have alpha is 10%, 5%, 2%, and 1%. So the confidence can be 90, 95, 98, 99. The significance corresponding will be 10%, 5%, 2%, or 1%. Okay, now for reasons which will become clear in a moment, we often talk about alpha over 2 as well, and that's simply just divide alpha by 2. So 10 divided by 2 is 5. 5 divided by 2 is 0.025. 2 divided by 2 is 0.01, and this is 0.005. I guess maybe I can fix that crushed up little alpha there. Okay, so alpha over 2 is those numbers. All right, so we're going to vary our calculations now and look at what happens when we change the confidence level, or correspondingly we change the significance level. So if you check your, pull out your normal table. So you should have a normal table in the front page of your textbook. You should be able to have that handy right now, or use the normal table that I included in your course's site. I think it was in the chapter 6 section, so you should print off that table and keep it handy at all times. You're going to need it repeatedly. The normal table will help us calculate how the margin of error changes as our confidence changes. So let's draw a picture, and this is a very commonly used picture. It's something I encourage you to do all the time, is to draw a picture. So here's our normal distribution. You see it's a really rough sketch. I don't care for super accuracy in it. And our X bar is going to be the kind of the middle of this one. We are going to go an interval to the left and to the right. And so this is, say, our confidence. And this was 95% of our measure of the time. 95% of the time, mu was in here. But now we're allowing this to vary. So instead of 95, I'm just going to make it 1 minus alpha. And so that means that there's a total of alpha percent in these two tails. And that means, since the tails are symmetric, there's alpha over 2 in each of these tails. Now, if alpha is 5%, the significance of 5%, that corresponds to 1 minus alpha of 95%. Alpha over 2 was 0.025. And now what I'd like you to do is to grab your normal table and find this number inside the body of the table. And so for me, it is exactly at negative 1.96 on the table. So you're going to find 0.025 on the interior of the table. Since it's a four-place table, it's going to be 0.0250. And you're going to look at the numbers. So this is a so-called reverse lookup that we've done before. Reverse lookup negative 1.96 is the number. So in this diagram, if alpha is 0.05, then alpha over 2 is 0.025, and this number is negative 1.96, and this number is positive 1.96. And so that's exactly where the 1.96 comes from in our earlier discussion. First I said it was 2, but then I changed to 1.96. So now we're going to look at what happens if this changes to 90%. If this changes to 90%, then this is 10%. This is 5.05 per 5%. And I'm going to look for that number in my table for 0.05. And it's actually somewhere between two values on the table, but you can do your reverse lookup. It's going to be between negative 1.64 and negative 1.65. So we're just going to average those two and make it, if alpha is 10%, then alpha over 2 is 5%. And the corresponding numbers here are negative 1.645. And because of symmetry, positive 1.645. Okay, and so these numbers are Z values. They're from the Z table. So they're called Z sub alpha over 2. So Z sub alpha over 2 in the first case was our familiar 1.96. In the 90% case, it was 1.645. And I'm going to ask you to do the next two on your own. They're not hard, really the same. If 1 minus alpha, if our confidence is 98%, then alpha is 2%, alpha over 2 is 1%. And find this inside the table. The corresponding value for Z sub alpha over 2 is 2.33. And 99%. And that one, again, is kind of between two values, but typically we just use 2.58. Okay, so this is an important table, just so you don't have to go through all the effort of looking up this stuff over and over again inside your normal table. This table is summarized in your formula sheet, and what it tells us is how do we vary our confidence interval calculation if we want to be more or less certain of our results. So let's go back to our question here, our 8.6, our dairy question. We are asked to do a 95% confidence interval. But let's do a 90, so back to 8.6 example. Let's do a 90% confidence interval. So most of the calculation is still exactly the same. The SE is always the same. It is approximately S over the square root of n. and that was 35 over the square root of 50, and that was 4.95, if I recall. Let me just jump back and make sure. Yes, it was. But now the margin of error is different. Because it's 90% confidence, I use a margin of error of 1.645. Pull up the calculator. 4.95 times 1.645. So it's 8.1428. Let's go 8.14. Okay, so our confidence interval is x bar plus or minus the margin of error. 756 plus or minus 8 point, what's the number again? Oops, 8.14. And so that is I start at 756, I subtract 8, it goes down to 748, 747.86 up to, I add 8, so I get to 764.14. There we go. Probably do better if you use a calculator than trying to do the arithmetic in my head like I do. All right, so there's my confidence interval. That is a 90% confidence interval. Now compare the 95% confidence interval for the same problem was, let's get the exact results here. Oops. 746.3 to 765.7. This interval here is wider. So if we're going to be more certain of our results, we make a wider interval. If we're going to be less certain of our results, less confident, we can make a narrower interval. So there's a trade-off there. And that trade-off is mediated exactly by this new number that we're talking about, z sub alpha over 2. So the more confident we are the more confident we want to be that our answer is correct, the wider we have to make our interval. Until, actually, if we were 100% confident, our interval width would be infinity. And so that's why we don't ever use 100% confidence, because it doesn't help us, it doesn't give us any information. Later on, we will talk about how to narrow the size of this interval and keep our confidence the same. Spoiler, we do that by increasing the sample size, by increasing n. But we'll get to that later in this chapter. That's just a kind of a preview. All right, so that is all the kind of big new information in chapter in section 8.4 is just this guy, this z sub alpha over 2. And that's what we do if we want to change our confidence from 95% to something else. We have to change our z sub alpha over 2 to something else. There's one other part of this chapter, and that is the population proportion. So the discrete version, if we have a situation where we're counting, then there's really only one change. That is in the calculation of So what we want is a confidence interval for P, true proportion. Of successes in the population. And so, following exactly the same reasoning, which I'm not going to bother duplicating, we have the confidence interval is P hat, which is the sample proportion, plus or minus the margin of error. The margin of error formula is, as before, z sub alpha over 2 times the standard error. And so the z sub alpha over 2 is for the, it depends on the confidence level, 90%, 95%, 98, 99%, whatever. Finally, SE, formula for proportion questions, is as it was in 8.2. It is the square root of PQ over N, and that is approximately equal to P hat Q hat over N. I'll take the square root there. Right, so that is how you solve these similar problems in the discrete case. The only thing that differs is this formula here. So everything else is exactly the same. Now there's one other little issue that I want to talk about, and that's sometimes this is not used even. So P hat Q hat over square root of N is our formula for SE. Sometimes we use an estimate for this. And it turns out that we want to find an overestimate for SE because we want to err on the side of widening our interval rather than narrowing it. If we widen it, we're still going to capture mu if we captured it before. Whereas if we narrow it, we might lose mu, or not mu, but P. Sorry, we might lose P. So we want to widen our interval. And so I'm going to estimate SE by this very crude estimate. There. So replacing P hat with 0.5 and Q hat with 0.5 gives me an overestimate for SE, and this is very commonly used. So I will later give you some examples of this. Which one do you use? Well, I would accept either one. You can use either one. There are some cases where we have to use the second one, and so that's why I really bring it up. I would say that if P hat is available to you, then maybe this would be a better choice, but it's actually not going to make too much of a difference in most cases to use this formula. Quickly, why does this work? Well, here's the graph of PQ with respect to P. So as P changes from 0 to 1, PQ follows this path, and you may be familiar with this from previous math courses called a hyperbola. And so the maximum value for PQ appears in the middle at 0.5. That's exactly why this estimate works. All right, so that's it for now. I think later on I may add some more examples which might help you. but for now I suggest you just turn to the examples in the problem set. Also take a look at the examples in the text of the main text of the textbook, and try them yourself. You'll benefit more if you try them yourself first, and then I show you some answers later. Okay, so good luck. Stay